Hi, BC Calculus Block F. I know you're thrilled that this is the lesson that you missed today. Hope you enjoy the video. Please send me an email or a text with any questions. I'll be in New Orleans, but I will do my best to answer them as soon as possible. So this is basically what I taught the class yesterday in Block C, so I hope you can follow along. What we're going to start off with here, and you can see that in the window I have a calculator, and the blue is the graph of y equals square root of x. The red is the tangent line to the graph of square root of x at the point 4, 2. And in F2 is the actual equation of the tangent line. So let's get that. So we get dy dx equals 1/2 x to the negative 1/2, which I'm going to write like that. And so the derivative evaluated when x equals 4 is equal to 1/4. So the equation of my tangent line is y minus 2 equals 1/4 times the quantity x minus 4. And if I clean that up so I can put it in my graphing window, I'm going to take that back and say it's 1/4 x minus 1 plus 2, so plus 1. Now my point here is, no pun intended, at the point 4, 2, the curve and the tangent line actually intersect. But if you can see here, and I'm not really that blown into this, that there are a lot of other values that while they don't equal each other or they don't intersect the line and the curve, they're pretty darn close. I mean, when you look at that, you really can't distinguish the red from the blue. And so what we use something like this for is to say, hey, what if I wanted to find the square root of 4.2? I don't know what the square root of 4.2 is, but let's see how close I can get. So if I put 4.2 into my line, I have y equals 1/4, and I'm going to go back to my point slope and have 4.2 minus 4 plus 2, and that gives me 1/4 of 2/10, which is 0.05. We can do a little better than that. 0.05 plus 2. And so the point on the line right here is, I'm going to take this up a little bit. In this slide, I'm actually on the line, and you can see that when I put in 4.2, I get out 2.05. So that's my approximation of the square root of 4.2. But if I go back up here and I'm on the curve, I'm within 1/100th. Now, I promise you that if we went out more decimal places, you would see a difference between the x-coordinate, the y-coordinate at 4.2 on the line versus the y-coordinate on the curve. But we're using the tangent line to get an approximation. And from what I've shown you here, we've got it within 1/100th, and maybe that's close enough, so you could really impress your friends with this if they wanted to know what the square root of 4.2 was. You could do a little tangent line, plug in 4.2 into the line, and there you go. Now, this only works for points that are close to the point of tangency. I mean, you can see here that using a point on the curve and a point on the line, those y-coordinates would be pretty far off. So the key is to get as close as possible. If I wanted to approximate the square root of 10, I wouldn't use the point of tangency of 4,2. I would use the point of tangency of 9, 3, and then I wouldn't be so far off. So the key with this is that you really don't want to get too far away from that point of tangency, or your accuracy, the further you get away, the more the accuracy starts to fade. One thing that's very interesting about this, and again, if we looked at more decimal places past the 0.05, we would see that our approximation is actually going to be greater than the actual square root of 4.2. You can see this from the picture. The line is above the curve. So if I have, again, we'll go back up to right here. If I have a curve and a tangent line, any point on the line is going to be greater than the corresponding point on the curve. And how can we figure this out without seeing the graph? It's with concavity. If your graph is concave down, there's no way you can put a tangent line beneath it. They're all going to sit on top. And if you have a curve that's concave up, it doesn't matter where you put that tangent line in, it's always going to be underneath the curve. So to show that you have an under or over approximation of the actual amount, what we're going to do then is just go to a second derivative. So if the first derivative is 1/2 x to the negative 1/2, then y double prime is negative 1/4 x to the negative 3/2. And since our values of x on the square root graph are all positive, then our second derivative for any value, not just 4.2, is going to be less than 0 because of this negative 1/4 in front. And from that, then we can conclude our graph is concave down, and our approximation of 2.05 is actually going to be greater than the square root of 4.2. Again, from here, from these two pictures, it looks like it's for 2.05 for both. But we know that the only reason that we're seeing 2.05 here is because I was lazy and didn't go out more decimal places. It would definitely be different than 0.5. Okay? Probably rounds up to 2.05. So that's really the main part of this lesson. And this was what I was hoping to grab you with, was with this picture, and hopefully I've done so. What I'm going to go into next is kind of a worksheet that I filled out in class for the class yesterday. I'm going to go ahead and do it with you. And then I have attached the worksheet that I gave them as homework to your actual assignment page. So if you'll go to your assignment page and click on it, you should have the link and you can download the homework. And then I will post the solutions. So not only will you have the homework, you'll have the answers. So when I see you on Wednesday, hopefully we're not going to have to start all the way over. It's pretty popular in calculus, especially AP, to not give you a function, but to give you values and see if you can conceptually figure out what's going on. And this is really kind of practical because sometimes life doesn't give you a function, but it will give you data. And we still want to talk about accumulating values and rates of change and all kinds of things that we've talked about so far with calculus. So I'm going to start off with a review between which two times does the IVT, and that would be the intermediate value theorem, guarantee that the amount of water in the tank reached 70 liters. And I remember yesterday I kind of went, duh, I picked a value that was on the chart. And so we changed this to 58. So I'm going to do that for you. So if you look between 7 and 9 hours after 7 a.m., we had to have passed 58 because to drain water out of a tank, you know it's draining continuously. You're not skipping over a liter. It's a very flowing, continuous type of problem. So because 58 is between 60 and 54, we can say by the intermediate value theorem that sometime between 7 hours and 9 hours after 7 a.m., that would be 2 p.m. and 4 p.m. So between 7 and 9 hours ace of 7, and 58, and ace of 9. So you could say that 58 is between, so I'll put that in English, between 7 and 9 hours. 58 liters is between A7, which is 60, and A9, which is 54. And I've left out the word that I need to say that ace of t is a continuous function. Now, something like this is tough to say unless they tell you. I mean, we even use the word continuously in this problem. How do you know that data is differentiable? Usually they will tell you. I think if they don't, you can assume that nothing is crazy going on. You don't have these spikes where, like, water's flowing out of some kind of a valve in the tank, and then somebody comes in and punches a hole and water spews out, and you don't have what I would call a smooth curve loss of water. You would have these spikes, and you would have something crazy would have to happen in order for this to not be differentiable. So when I say ace of 2 minus ace of 0 over 2 minus 0, if we were connecting points, that would be the slope of the secant line. But I think it's safe to say that that is the average loss or decrease of water in liters. Notice this says use correct units in your answer. So just don't say of water, use the units of water. The average loss of water in liters in the tank from 0 to 2 hours. And then if we actually compute that, that's 70 minus 80 over 2 minus 0. And if they ask for that, then that would be -5 liters per hour. Okay, so we would call that an average loss of water over a unit of time. Use the table to approximate a prime of 5. And this gets a little bit ambiguous. I'll be real honest with you. You know that if I put the limit, instead of delta x, I'm going to use delta t approaches 0 of ace of t plus delta t minus ace of t all over change in t, that would give me a prime of t. Definition of the derivative in context. If I change this to a prime of 5, then I'm going to change my t's to 5. So the limit as delta t approaches 0 of ace of 5 plus change of t minus ace of 5, and ace of 5 is 66 over delta t. And that is the actual value for a prime of 5. The problem is delta t can't go to 0 here. The best I have to offer, I don't know why I went out that far, is 2. If I go on this side, the change of t is 3. If I go on this side, the change of t is 2. So the best approximation of ace prime of 5 here would basically be 60 minus 66 over 7 minus 5. So I would get -6 over 2, or -3 liters per hour. And that's how to approximate a derivative given values on a chart. And we will work a lot more with that. There's a little bit on your homework worksheet, but not much. And then this last problem really falls into line with the majority of your homework. The